Welcome. In this video, I wanted us to go back to talk about the resolution of a vector into its components. It's basically finding the x component and the y component of a given vector. But I want to talk about this in depth so that we're able to figure out exactly what is it that we're doing when we're finding the x component and the y component of a vector. This will be a good basis for us to generalize this idea. Once we fully understand what it is, what are the mechanics of finding the components of a vector. So over here, I have a vector which is located in some coordinate system. Our coordinate system has an y component and an x component, and anything along the side-to-side direction is going to be the x, anything along the up-down direction is going to be the y. Now, what we need in order for us to find the components of this vector v bar, we need two ingredients. The first one is the magnitude of this vector, so the length of this arrow, that's the first ingredient. The second ingredient is the angle that this vector makes relative to either one of these coordinates or axes. So let's suppose we were to insist that the angle between the vector and the x-axis is theta. The mechanics of us finding the x component basically consists of us first forming a right angle triangle which encloses the angle theta, the angle which we know. So how do we form a right angle triangle which contains this angle theta? Well, the mechanics of it is that we would drop a perpendicular. Notice that the perpendicular comes from the tip of our vector. So the way we enclose, or the way we form this right angle triangle, is that the vector itself, the length of the vector, must form the hypotenuse of that right angle triangle. And number two, that triangle must contain the angle which we know. And the fact that this dotted line is a perpendicular, this already tells us what that angle is going to be. It's going to be a 90 because obviously it's a perpendicular. Now we have all the necessary information in order for us to find the x component. Notice the x component is going to be this side of our right angle triangle. And let's label this side as v sub x, and the y component is going to be this side of our right angle, and let's label it v sub y. The side v sub y is opposite to the angle, so it plays the role of the opposite side in this right angle triangle. Whilst the side v sub x is close to the angle, but it's not the hypotenuse. So we call this side the adjacent side. And now we can use the familiar trig ratios that enable us to find the opposite side to the angle and the adjacent side to the angle. So let's go ahead and write these down. We can immediately go and say v sub x is going to be the magnitude of vector b. Remember, the magnitude, basically the hypotenuse, times the cosine of our angle theta, and the y component is going to be v sub y. It's going to be the magnitude of vector v, which is the hypotenuse of this triangle, times sine theta. So this is how we found the components of our vector, of vector v. The necessary ingredients were that we needed the angle. We needed to know the angle which our vector makes, angle of the vector, let's say relative to some axis, to one of the axes. Let's say relative to some axis. I'm going to stop here. The angle could have been either here or there, but the point is we needed the angle. Once we had the angle, we could therefore complete or form a right-angled triangle. This was ingredient number 2, right angle triangle. However, the right angle triangle had to be made such that the vector forms or is the hypotenuse. The vector itself is the hypotenuse of the triangle. Or maybe let me not do that. Of the triangle. That's important. So if the hypotenuse is, well, if this vector is to be the hypotenuse, this means the way we form a right angle triangle, we must drop a perpendicular from the tip of the vector. The vector whose components we're looking for will form the hypotenuse, so we drop a perpendicular from the tip of that vector. And as we have here, and once we had these two ingredients in place, we were able to find the y component and the x component of our vector. This is true when we are finding the components of a vector relative to some coordinate system. So this is some fixed coordinate system. Now, how do we find the components of a vector relative to another vector? In other words, how do we resolve a vector relative to another vector? Well, this is the idea. The idea is exactly the same. We're going to also look for these two ingredients. The angle that the vector makes, this time not to some axis, but relative to the other vector. So let's go ahead and generalize this idea. So in this case, we have two vectors, vector v and vector p. Suppose we are looking for the components of vector v relative to vector p. Another way of saying this is we are looking for the component of v as projected in the direction of vector p. Again, what we're going to need is the angle between the vector we are interested in and the direction or the axis onto which we would like to project it. And in this case, it's applied to us as theta. Now we need to form a right angle triangle in which this vector we are interested in, which we seek to project, that vector needs to be the hypotenuse. And the right angle we form needs to enclose this angle. So this guy needs to be the hypotenuse, and the right angle triangle needs to include this angle theta. So the best way, or well, the only way to do this is to drop a perpendicular from the tip of our vector v. So therefore we will have the 90 degree there because we insisted that this should be a right angle triangle. So notice in this right angle triangle, the hypotenuse is the vector v, and it encloses the angle, the angle between the vector of interest and the vector onto which we're projecting. So now, notice that this side here of this triangle is going to be the side that's adjacent to the angle. Basically up to here. This side is going to be the side adjacent to this angle, and the dotted line, this side, is going to be the side that's opposite to the angle. But notice this side here is parallel to the purple vector, to vector p. So let's call this side, let's give it a name. Let's say it's v parallel, maybe I shouldn't, let me say it's v parallel to p. So that's the horizontal side, or maybe this side here. And this side, the dotted line, is the side opposite to this angle, but also this side is perpendicular to the purple vector, vector P. So let's also give it a name, call it V perpendicular to P. It's the part of P that's perpendicular, it's the part of vector V that's perpendicular to vector P. So now let's find the expression of these vectors, of these components. Oops, let me go back to the pointer. Now we are interested in understanding how can we find these two. Let's go ahead and express. Remember, V parallel P, this thing, V parallel P plays the role of an adjacent side in this right angle triangle, and we know the proper trig ratio that relates the adjacent side to the hypotenuse. That's the cosine. Cosine of what in this case? It's the cosine of this angle, theta. So let's write down what cosine of theta is going to be. It's going to be the adjacent side, which is V parallel P. So it's going to be V parallel P divided by the magnitude of V bar, because the magnitude of V bar is our hypotenuse. So we can write that down and say V bar. And let's make this guy the subject of this formula. We find that V parallel P bar is nothing more than V bar cosine of theta. Notice, this is not the x component of V bar, because notice in this there is no x coordinate. There is no coordinate system. We are not finding the components of a vector relative to a coordinate system, but we're finding the coordinate of vector V relative to another vector. We are projecting this vector onto another vector, not to some coordinate system. Okay, so let's go ahead and find the component of V that's perpendicular to vector P. So basically this side. This side, which is represented by the dotted line here, is opposite to this angle. So therefore the appropriate trig ratio to determine that side is going to be sine of theta, where the opposite side is V perpendicular to P bar, divided by the hypotenuse, and our hypotenuse here is V bar. So therefore, we make V perpendicular to P, we find that V perpendicular to P bar is going to be the magnitude of V times sine of theta. So whenever we find the projection of one vector onto another, we are doing exactly what we have been doing, except now we're not projecting onto some coordinate system, but we're projecting this vector onto another vector. However, the procedure is exactly the same. What we need is the magnitude of our vector and the angle, and that enables us to find the sides that perpendicular, the part of V that's perpendicular to vector P, and the part of V that's parallel to vector P. Now, obviously we can always calculate this if we knew this, this angle theta, and we knew the magnitude of vector V bar. We could simply plug in the values here and we would find this value. We could find what V perpendicular to P is and V parallel to P is. Excuse me. Now the question is, what happens if you are only supplied these vectors P and V in unit vector notation? How would you find this thing here? Well, there are some definitions, or there are vector multiplications that enables us to find this almost directly. Let's consider, what is the dot product between V bar and P bar from definition? From definition, V bar dot P bar, this is the dot product, and by definition it's the magnitude of V bar times the magnitude of P bar times cosine of theta. Now, we can reshuffle this formula here and move the V bar here. We haven't done any, if we do so, we're not violating any mathematical consistencies. We're just swapping two values around. We say V bar cosine of theta. Now, this thing here, V bar cos theta, is equals to that. So we can substitute this thing here and plug in this value. Instead of V bar cosine of theta, we can put in V parallel P bar. So therefore, we can rewrite this as P bar times V parallel P bar. Now, which means V parallel P bar is going to be given, therefore, this means V parallel P bar is going to be V dot P divided by P bar. So basically what I've done is I've divided by P bar in order to isolate this thing here. So if the odds are on our favor, that is, we have the magnitude of V and the angle theta, finding this V parallel P bar is simply substituting things here, the values here. However, if we don't have the angle, especially in 3 dimensions, we don't know the angle, the easiest way to find this thing here is by using the dot product between these two vectors and dividing by the magnitude of the vector P. Notice vector P is the vector onto which we are projecting the other vector V. These two things are equal. V parallel P bar is either equal to this, is both equal to this and equal to that. So these are two alternative ways of finding the projection of one vector in the direction of another. What about the projection of a vector, the component of a vector that's perpendicular to another? So remember, vector V will have two components. One component will be parallel to vector P, and the other one will be perpendicular. So how would we find V perpendicular P? The way we would find that is from the definition of the cross product. Remember, the cross product is by definition, maybe let's copy this, move this over. Actually, I'm going to need to move this much. Bear with me. I'm going to need to move this much just to keep things in context. So let's paste. Great. So now remember what we want to talk about, what we want to find. It's this part, the part of V that's perpendicular to vector P. That is given by this thing here. And as I've said, if the odds are on our favor, that is, we have the angle between the two vectors and we have the magnitude of vector V, we could simply plug and play here. We could simply plug in the magnitude of V and the angle between them, and we would be done. That will give us the part of V that's perpendicular to vector P. However, sometimes in 3 dimensions or higher, we don't know the angle between the two vectors, but the vectors are supplied to us in unit vector notation. So this is where we use the definition of a cross product. Remember that the definition of a cross product of V cross P, that's P. V cross P, the magnitude of this is given by the magnitude of the first vector times the magnitude of the second vector times sine of theta in this case. This is definition. Remember what we called this combination, the combination of V bar sine theta. We gave that a name, and that name was, we gave it a name, we call it V perpendicular to P bar. So if we are interested in finding V perpendicular to P bar, we can simply divide by P bar in this situation, This will give us, therefore, v perpendicular to p bar is simply going to be the magnitude of the cross product of vector v with p divided by vector p bar. So, whenever you are given vectors in unit vector notation, or you don't know, and you don't know the angle between them, the way you would find the component of v that's perpendicular to vector p is by finding the magnitude of their cross product and dividing it by the magnitude of vector p, where vector p is the vector onto which we are projecting, or against which we are projecting. So I hope this gives you a bit of an idea. Just to change things up a little, I'm going to do this a different way in the next video to try to demonstrate this procedure again. I'm going to reuse this vector, this scenario, but to avoid being too long in this particular video, I will stop here. The next video will simply be to reiterate things, but in a different context. So I'll stop here and see you in the next video.